Okay, so let me introduce you. So the next speaker is Professor James Peter. He's from University of Manitoba from Turkey, and the title of his talk is Several Forms of the Geometric Lusternik Schnirel'mann category. Okay, so you are welcome.
Thank you very much. Incidentally, it's 6 o'clock in the morning here, and I see it's afternoon there. So you are fortunate to be wide awake while I'm just waking up. Well, then, before we start, I want to mention first that having this conference is great. It's wonderful what you've done and all the work that you've done in setting up this conference, making it possible for us to get together from different countries. And then I'd like to dedicate this talk to Professor Nampally. He was a pioneer in proximity space theories that Professor Verghili mentioned, and also Professor Saroja. She's a retired professor from Osmania University in Hyderabad, India. It's always difficult when a professor in mathematics has to retire because of the system that she's in. And that was the case with Professor Saroja. Let's see if I can get this thing working. Oh, there you are. Here's an outline of the talk. I first remind everybody about homotopic paths. And considering the previous talk, this is something that all of you know quite a bit about. And then the notion of covering also is given as a reminder, with one exception. This Professor Nagura Shakamoto and Tanaka recently introduced the notion of a good cover, which is appropriate in looking at the definition of a geometric category. And then the last is an application. The application is reminiscent of what Professor Verghili showed, except that instead of looking at multiple frames, as in Professor Verghili's case, we look at a single frame and its triangulation. See if I can get this working. Oh, there we are. Okay, I have to get the right buttons. Here we have a homotopic path. There's a continuous mapping, and this is the simplest form of a homotopic mapping from the unit interval into a space K. Letter K was the way of J.H.C. Whitehead.
Professor, we cannot see your slide.
Excuse me, your slide disappeared. So could you fix this?
We're working on it.
Okay. Yeah, sorry for this.
How's that?
Okay, now I see. And what about us?
Okay,
Yes, we
great.
can.
Is everybody could see now? Because I'm able to see it.
Yes, we can.
Okay, so please continue. Okay, thanks.
Thank you very much.
No,
Well,
you're welcome.
okay, then anyway, actually all of this comes back to Whitehead's work in 1949 on homotopy systems. And this notion of CW space that Whitehead worked in, it leads to the notion of, in his space, you had things called zero cells, which would be called, which have a geometric realization as points in a Euclidean space. And then we have the notion of a homotopic class. And I use the term homotopic path class as a collection of homotopic paths denoted by bar H bar H bar H bar for a path or a set of paths with the same endpoints. Okay, and here's an example where we have three paths that construct the sides of a path triangle where the sides of the triangle are these continuous maps, the result of continuous maps, one point to another in a triangle. And this path triangle maps to its geometric realization in a familiar planar triangle. And here's an example. Here are three path classes, H, K, and L. And notice that the classes themselves form what could be viewed as a collection of overlapping path triangles. If you follow one of the paths, say H1 to K1, H1 to K1 and K1 to L1 and L1 back to K1. And this is a theorem from Whitehead, 1949, and this is it's an extraordinary theorem in its simplicity and its reach, namely that a given homotopy system, such as the ones in the previous slide, each one has a geometric realization if the dimension of the systems is less than or equal to 4. The problem would come in if we started considering dimensions higher than 3. And then there's this paper that where a lemma was introduced, where every homotopic path has a geometric realization as an edge. Edge in the sense of a line segment in the Euclidean plane or on a Riemannian surface. And then the proof sketch is straightforward, where the homotopic mapping is from the unit interval to the Euclidean plane. And so a point, an edge in the homotopic space in Whitehead sense has a geometric realization in an edge in a Euclidean sense. And here's an example where you have a path triangle and this path triangle, notice, has a non-empty interior. That's an assumption that's made here. And then this path triangle maps to a triangle in Euclidean space or Riemannian space. And the notation H triangle E moves over to the notation for its geometric realization bar H triangle E bar. And here you have a pair of paths. You might call them path triangle systems because we have systems of homotopic maps that form path triangles in a CW space. And it's that system's geometric realization in a Euclidean space where you have bar square bar H triangle E bar in the Euclidean space. Now, what's important here and what's interesting is that the curvilinear lines from the vertexes V1 to V2 to V3. The main thing is that we allow for not only straight edges, but also curvilinear edges in the geometric realization of these homotopic maps. That's appropriate since homotopic maps in general have curvilinear realizations. Okay, and here's the notion of a cover. Okay, this is a very old notion. And it just means that for a space X, you can have if it has a cover, there is a collection of subsets in the space such that the space is a subset of the union of those subsets. Now, what's interesting here is the notion of a good cover, which is entirely appropriate if we're going to consider a Lusternik, a geometric realization of a Lusternik Schnirel'mann category. Here, a good cover is a space X has a good cover provided. There's a collection of subsets in the space such that X is a subset of that union of those sets. The intersection of is finite and contractible. And the notion of contractible is new in the notion of a cover. Here's an example of what I consider a good covering. You have a geometric realization of a path class. And what we have in this geometric realization is a collection of homotopy curves that overlap with an ordinary triangle. And the ordinary triangle is a subset of the union of, if you have enough of them, you have to have enough of these maps to make it work. Then the triangle is a subset of the union of those homotopic maps or curves. The other thing to notice here is that the maps themselves, the geometric realization of them, each one is contractible. Okay, then we have the notion of an LS geometric category. And this is from Montejano in 1986, but only really got a lot of attention recently in an AMS monograph, I think it's 2008, from Cornelia Lupton, Apria, and Tonray in an AMS survey. The notion here is that the geometric category of a space X is the minimal covering of X with contractible open sets of X. And then we have a lemma that this lemma is part of four lemmas that lead to a result in this talk and then this work. Mainly that if you have a homotopic sinusoidal curve in either the CW space or its geometric realization, the geometric realization of that path of a homotopic path class H is a planar sinusoidal curve. And here we have examples. The example of this paper is that if you have a triangle in the Euclidean plane, it's going to be a subset of the minimum of the interior of the path class in this. And this turns out to be a geometric category of that triangle, which is the minimum of the interior of those path classes, geometric realization of path classes. Okay, then they have conjectures which are recent and still need to be verified, namely the tangent field of a path, the geometric realization of a path is in fact the basis for a geometric category. And similarly, you have the conjecture that if this is for the tangent field, and similarly, if you have a vector field, you have a similar result. And here's a lemma that tells us that if you have a homotopic path in a space K, every path is contractible And there exists a minimal geometric realization that path of that path class with the same boundary endpoints, such that the path class covers its geometric realization as a triangle in the space. And then every planar triangle in K has a minimal covering. And the theorem is that there exists a geometric category for a triangle in the Euclidean plane that is the minimum of the interior of these homotopy classes, such that the interior of the homotopy classes is a covering for the triangle. And now we have a definition for a cluster of triangles. This definition is motivated by the application, which requires a cluster of triangles instead of just one. And the corollary is that the geometric category for a geometric realization of a path class is, if you have that, if there exists one of these categories, then the minimum of that geometric realization of the path class is a covering for the collection of triangles in the space. And this is an example where you have a triangle cluster covering. As if you continue the maps from the vertices of the different triangles in the cluster. A cluster meaning that the triangle and the cluster have a common vertex. And moving ahead, because I'm running out of time, we want to look at Delaunay triangles and consider a geometric realization of triangle clusters. This is kind of remarkable because we're moving from the abstract triangle clusters in a homotopic space in Whitehead sense to a collection of triangles that are in a Euclidean space. So here's an example. This is competing with Professor Farley-Gillies' example, where you have a video frame of a school bus on a winter street in downtown Winnipeg from 2 years ago. And it's triangulation. And notice that the cluster of triangles that have yellow edges, the interior of those triangles covers the bus. And we can move ahead and say, with the central vertex P. So we can easily move to the result we had, namely that we can argue that we have a geometric category for that triangle cluster. Well, okay, I want to thank you very much for giving us an opportunity to present this paper. And I want to mention that here are papers that are related to what was discussed, including the paper with Professor Regilly that was published in the Applied General Topology Journal in 2023. And that concludes my talk.